Okay, so I said 103, 102, it's close enough. Anyway, so last time I'd mentioned that one more thing we needed to talk about in Chapter 4 before moving on to eigenvalues and eigenvectors is change of basis. So this will not take us that long to talk about because we've already seen the simpler example of change of basis, and this is very similar. So as I mentioned last time, you've already seen the example of changing a change of basis where the two bases in question were some generic given basis B and the standard basis of Rn, right? So we already got to see that, and the the only thing we've yet to see in this kind of situation that arises is a change between two bases, neither of which are the standard basis. So, for instance, maybe, so I should say the idea, similar to before. So before, when we talked about change of coordinates, or we didn't necessarily call it a change of basis, even though that's what it was. So similar to before, but instead of changing between, say, a basis B and script E, which is the standard basis. I'm not going to use this that much. Textbook writes it like this sometimes, but when I say standard basis, I'm usually going to list out the vectors. So this is the standard basis of Rn, sorry. Okay, so similar to before, but instead of changing between a basis B and the standard basis of Rn, we change between bases, say, C and B. So maybe I'll start out just C, B and C, where B and C are bases of some vector space V, some generic bases of a vector space V. So the idea, the setting here is that you have a vector space V and you have two distinct bases of V, B and C. Okay. We have known since like the first section of chapter 4 that a vector space can have several bases, right? And I could even ask you if I wanted to come up with, say, multiple different bases of Rn, right? There's definitely not just a standard basis. There's, in fact, you already know one of the equivalent conditions from the invertible matrix theorem tells you that if you can find three linearly independent vectors, right, in R3, then you have a basis for R3, right? So pick any three linearly independent vectors, they're automatically a basis for R3. So that right there gives you a ton of different bases. Now, for a generic vector space V, there is a question that I could ask that is not covered in this textbook. At least I don't think so. Last time I had a look at it, it's not. Maybe in the newer editions it is. I'm not sure. But this is more of a, turns out this is more of a philosophical question, which is, does every vector space have at least one basis? So you might think the answer to that has to be yes. And for the math that you are, statistically speaking, for the math that you are going to do, the answer is yes. But it turns out that whenever, and yeah, someone said an infinite a number of possible bases. Of course, yeah. So in R3, you can literally come up with infinitely many distinct bases of R3. Any three linearly independent vectors will do in R3. So, if you have a 3x3 matrix that's invertible, right? Any invertible 3x3 matrix, take its columns, that's another basis of R3, right? But the question of whether or not every vector space is guaranteed to have at least one basis, we don't need that for this course, because every example we're going to deal with, we're going to be given a basis, or we're going to be in a setting where we know a basis. But it turns out that question is equivalent to something called the axiom of choice. Is it equivalent to, or does it just depend on having the axiom of choice? Now I'm confused. But all I know is that in order to get it, I need something called the axiom of choice, which we will say that we assume. Okay, this was controversial maybe 100 years ago, but it's not anymore. But that is probably one of the reasons. I mean, maybe it's in some offhanded comment in the textbook I just haven't seen. But that's a more philosophical question. So you can assume that every vector space has a basis, although for the questions that you are doing, you won't need that assumption. You'll be given a basis to work with if you need at least one. But it's an interesting thing. So if you're interested in that, you can look it up. Just type into your favorite search engine, does every vector space have a basis? And you will be met with all kinds of interesting things. Okay. So, for our purposes, we'll say every vector space has at least one basis, right? All right, so B and C, that was went off on a little bit of a tangent there, but that's okay. That was, it's a worthy thing to talk about. So here I have two generic bases, B and C, for some vector space V, and I want to switch between them. So as an example here, maybe I should restart my paper so that I have full space on this one page. So here's an example. So consider bases, say B, which is B1, B2, and C, no, I don't want to. How do I want to do this script C? Oh, I should loop it like that. There we go. So that I don't do something like a zeta or a c. So I have two bases, B and C. So I've just labeled them completely generally. So B1, B2, C, and C1, C2 for a vector space V. Okay, such that I actually have a way of expressing each of the B basis vectors in terms of linear combinations of C. So the basis vector B1 is 4C1 plus C2, and the basis vector B2 is minus 6C1 plus C2. Okay, suppose that X is then expressed in the B basis, which is 3B1 plus B2. Okay. So find the C coordinates of X. Okay, so let's refresh our memories on what C coordinates are here. Okay. So when you have a basis, what are these bracket coordinates that you talk about? Well, here's a good example. So X is given to me as a linear combination of these basis vectors, so 3B1 plus B2. What's another way of saying that? So i.e., another way of saying this is that the B coordinates, right, of X are what? Well, 3, 1. Right? That's how we defined B coordinates, right? For some basis B, right? This was when we talked about change of coordinates between standard basis and a generic basis. This is what we meant by B coordinates. So the idea is it was just finding the weights, right, in a linear combination of some vector in turn or relative to that basis that you're finding the coordinates of, right? Okay, so this is B coordinates then. So the idea is I'm given B coordinates and I want to find C coordinates. So this situation I'm given, essentially I am changing from B coordinates to C coordinates. So a change of basis is a change from, B coordinates to C coordinates. It's a change of coordinates where your coordinates are two different bases, right? And one of them is not necessarily the standard basis. All right, but then how do I do this? So the idea here is I actually have B1 and B2 written as linear combinations of the C basis. So actually, before I even get into this, I can just write, so note that X is 3 B1 plus B2, but B1 and B2 are both given to me as linear combinations of C, so I can actually just plug those in, right? This is 3 times 4C1 plus C2 plus B2, which is minus 6C1 plus C2. Okay, and so going through some algebra here, this is 12C1 plus 3C2 minus 6C1 plus C2. Okay, and so simplifying here, what do I get? 12C1 minus 6C1, so that's 6C1. Plus 3C2 plus C2 is plus 4C2. Well, so this is a simple way of doing it. So then I found my C coordinates, right? So my C coordinates here is just 6, 4, right? Okay, so that's one way of doing it, right? Now, this I was able to do, and the algebra wasn't too bad because there was only 2 of these vectors, and I had the benefit of actually being given this linear combination, in a nice form. So I already started with both basis vectors of B being given to me as linear combinations for C. So actually, I already had the C coordinates for B1 and B2. So what is it that is actually going on here? So this is maybe the most straightforward way that you would write this out. But what I'm going to do here is redo this. Okay, I'm going to redo this real quick. And instead of just jumping straight to this, I'm going to rewrite it and show you what it is that's going on. So it doesn't really make sense to, someone said set augmented matrix with B coordinates. That's exactly what I'm going to do. So in this setting, like I said, because the algebra involved to get here was simple, because I was given everything I needed and I didn't really have to do that much. This is doing it this way and seeing it this way is not always the most useful way of thinking about it, because in a more general setting, it just wouldn't work out as nicely. So what I'm going to do is show you, it seems to be a more kind of roundabout way of doing it, but it's actually like the nice, like most organized way of getting this answer. Okay, and so what do I want to say here? So let's again, maybe not totally restart paper. So I'll just continue here and continue on to the next page. So let's do it another way. So going back to our X, if I want to find C coordinates of my X, that looks like an E. That looks bad. My C is too curled here. So this is a C. Maybe I'll rewrite it. So here's there. Okay, there's my script C. Okay, so my C coordinates of X, well, that's the C coordinates of 3 B1 plus B2. That's my C coordinates. Okay, well, how does the coordinate map work? The coordinate map is linear. In fact, the coordinate mapping is an isomorphism, so it's as nice as possible, but in particular, it's linear. And so I can actually rewrite this as 3 times the C coordinates applied to B1 plus the C coordinates applied to B2. Okay. But of course, I can rewrite this as a matrix equation. So the matrix equation that I can rewrite this as is the C coordinates of X are equal to a matrix that has two columns. So the first column is the C coordinates of B, or sorry, of B1, and the second column is the C coordinates of B2. And I multiply that by the vector 3, 1. But what was the vector 3, 1? The vector 3, 1 is actually the B coordinates of X. So really what we're writing here is a matrix that has columns. The first column is the C coordinates of B1. The second column is the C coordinates of B2. And then this vector that I'm multiplying by is the B coordinates of X. Okay. Now, what do I want to do? So I'm going to look here for a second. I actually know what these quantities are, but I want you to see that the C coordinates of X, oh, I'm pointing to something a little bit off the screen now. So the C coordinates of X are equal to some matrix, the columns of which are the C coordinates of the B basis vectors, times the B coordinates of X. So what is this matrix? This matrix is going to be my change of basis or change of coordinates matrix from B to C, because multiplying by this matrix on the left, this B, the B coordinates, gives me the C coordinates. So this is going to be the matrix P from B to C, and the arrow is going backwards. Why is the arrow going backwards? It's because I'm multiplying on the left, so I'm taking B to C. That's why I'm writing this going backwards like this. So I'm going to restate this more generally when I give the theorem for how to do this thing. But I want to rewrite this in one more way. So we actually know what these things are. We know what these things are. What are the C coordinates of B1? Well, the C coordinates of B1 are 4, 1. And the C coordinates of B2 are minus 6, 1. And so I can rewrite this in my example. So continuing my example, my C coordinates of X are my C coordinates of B1 are 4, 1. And my C coordinates of B2 are minus 6, 1. And this is times 3, 1. Right? But if you multiply that, what do you get? Oh, you get 6, 4. Okay. Now again, this seems like a needlessly confusing way of doing it in this case, and it is for a simple case like this, but this allows us to see what's actually going on. So what is actually going on? The main theorem in this section is the following. So let script B be a basis for a vector space V. We'll say there's n of them. Okay, and C, of course, because they're both bases for the same vector space, they have to be the same size. So let script B and script C denote two bases. They each have n elements, so be bases of a vector space V. Then there is a unique matrix that is n by n called the matrix P from B to C such that the C coordinates of X are equal to the matrix P from B to C times the B coordinates of X. Okay. All right. The columns of this matrix P from B to C are the C coordinates. So these are the C coordinates, or the C coordinate vectors, we'll say. So the C coordinate vectors of the vectors in the basis B. Okay. All right. i.e., another way is, as we've written earlier, this matrix P from B to C is the matrix whose columns are the C coordinates of the B vectors in the order as listed. Okay. This matrix is called the change of coordinates matrix from B to C. Note, this is extremely similar. I mean, not just similar. This is literally the same matrix that you had before when you were changing coordinates. The only difference is that one of these bases is not guaranteed to be the standard basis of Rn now. Okay. Okay. And yes, so someone said, isn't this kind of the same thing we did when we transformed the identity matrix? So yes, this is essentially what we did before, only we have slightly generalized this setting where the two bases in question are just generic bases of a vector space. So B and C, neither of those need to be the standard matrix, or sorry, none of these need to be the standard basis for this to make sense. Okay. So you might automatically get intuitively there's another thing. So first of all, here's a quick rundown. I'm not going to write this out. I'm going to go through it vocally. So if you need to later, rewind this part, that's fine. But here's the next thing I'll say. So let's think about the properties that this matrix might have. Okay. So this matrix, it has columns determined in this way. How do I get the C coordinates of these B basis vectors? Well, they're coordinate vectors of a linearly independent set, right? Because B is a basis. So the vectors in B are linearly independent. These are coordinate vectors of a linearly independent set, right? So C is also a basis, but forget about that for a second. So B is a basis. The vectors in B are linearly independent. These vectors that make up the columns in this matrix are coordinate vectors of a set of linearly independent vectors. So they're linearly independent. Okay, they have to be linearly independent. So this is a fact you can prove if you want. In fact, I don't think I gave this to you as homework, but I think it's an exercise in one of the earlier sections we did. Anyway, it can be shown that if you have a linearly independent set, not even necessarily just a basis, but if you have a linearly independent set, if you apply the coordinate map to that, to those vectors, what you get as vectors, those coordinate vectors, are also linearly independent. So the columns of P are linearly independent, so it's invertible. Okay. Note, this change of coordinates matrix is invertible. So the change of coordinates matrix from B to C is invertible. It is invertible. So let's rewrite that key thing coming from the theorem here. And this is the main thing that you should remember. So maybe I should go over this. What should you remember? This is the key thing that allows you, it is the relationship between these things that allows you to swap back and forth. And of course, you should remember how P is defined, although that's not that tricky because this is essentially the same P that we used before for our more restricted change of coordinates. But you should remember these two statements, right? You remember these two statements, then essentially you remember all the words. You remember how to get from B to C. Okay, so rewriting that same condition, the C coordinate vector is the product of the B coordinate vector on the left by this matrix that changes coordinates from B to C. But since this is invertible, I can multiply on both sides by its inverse. And what do I get? I get that the inverse of the matrix that changes coordinates from B to C times the C coordinate vector is equal to the B coordinates. That is, it's equal to the B coordinate vector. Yeah, and someone mentioned, and thus the inverse will give you the other change of coordinates matrix, i.e. the change of coordinates going the opposite way. So look at this expression, right? So look at this expression. This expression tells me that if I want to know what matrix I can multiply the C coordinate vector on the left by to get the B coordinates, it's the inverse. i.e., this statement tells me that the change of coordinates matrix from C to B is just the change of coordinates matrix from B to C inverse. Right? Yep. So someone already noted in the chat, this is exactly what's going on. Okay. All right, so going back and forth here is no problem. You're using the fact that these are bases, so these aren't just some generic sets of vectors, right? These are the nicest possible sets of vectors, okay, for these things. All right, and so one thing I wanted to do, and yeah, I'm going to do another example here. So let's see how we might deal with finding, say, a change of coordinates matrix between two bases. We can even do it in the Rn case, okay? Because this is actually going to give us, this is going to involve kind of some ways of computing with these vectors that you might not have done yet. I can't remember actually if I'd given you back in chapter 1 an example of where you would have done it this way. But let's do one more example. So let's say, what if I have, so let's let B1 be the vector -9, 1, and B2 be the vector -5, -1. All right, so they're not scalar multiples of each other in R2. That tells me they're linearly independent and thus a basis of R2. And let C1 be 1 - 4, and C2 be 3 - 5. Again, it's a set of two vectors. They're not scalar multiples of each other, therefore they're linearly independent, automatically a basis of R2. So, and consider the bases script B, which is B1 and B2, and script C, which is C1 and C2 of R2. Okay. All right, so let's find the change of coordinates matrix from B to C. Okay. So how do I do this? So here is where immediately I run into an issue where a lot of the work that was done for me before is not done here. So this is what I meant by computationally, you come across a situation that, like I said, you may have come across before in chapter 1, but what is it I'm talking about? Let's go back to our first example. Why was our first example so straightforward in finding this matrix, right? Or I mean, even skipping straight to finding a coordinate vector we wanted. Because I was already given B1 and B2 in terms of the C basis, right? So I already had B1 and B2 written as linear combinations of the basis C. I already had the C coordinates for B, right? I was actually given, what was this in our previous example? Well, this was just another way of writing this was I was given the C coordinates straight up, right? So the C coordinates of B1 are 4, 1 in this example, and the C coordinates of B2 were minus 6, 1, right? I was just given that immediately. Okay, and so in terms of finding the matrix, I was able to write it immediately. It's just, these are the columns, right? There's the first column, there's the second column. So that's why this was so straightforward, because it was already, all this work was done for me. Right here, that's not done. I'm just given 4 vectors, right? So the B vectors are in my basis B, the C vectors are in my basis C, and I'm asked to find the change of coordinates matrix. So how do I do this, right? So I need to solve some equations, right? So I need to be done, right? I need the C coordinates of B1. And I need the C coordinates of B2. So here, let me demarcate here. So here's my statement of my example. My solution is I need these two things. I need these two quantities. Right? I need the C coordinates for B1. I need the C coordinates for B2. Okay, so how do I get those? Well, my C coordinates for B1 means i.e. I need weights. So I need weights, say, x1 and x2, such that B1 is equal to, say, x1 C1 plus x2 C2. And I need weights, say, y1, y2, such that B2 is equal to y1, c1 plus y2, c2. Yeah, exactly. So Gustavo said in the chat, this is what I'm looking for, right? I'm looking for exactly these expressions. But of course, I need to, what do I need to do if I have 2 vector equations, right? I want to solve them simultaneously. If I transcribe them on their own, what I get is exactly, the matrix that has column C1, C2 times my vector x1, x2, right? That's my vector B1, right? So that is equal to B1. And so that's what I get from this first vector equation. The second vector equation gives me the same matrix, C1, C2, times my weight vector y1, y2, and that's equal to B2. So I get two matrix equations there, right? Okay. But I have two matrix equations. Could I solve them separately? Yeah, absolutely. But there's a more efficient way of doing it. I can actually solve them simultaneously, right? And so this is the computational trick I said that, you might have seen the homework of chapter 1. So to solve these simultaneously, what do? So I set up an augmented matrix that is C1, C2, and B1, B2. Right? And what do I do with that matrix? Well, so let me write it out first. So C1 is 1 minus 4, and C2 is 3 minus 5. And then the B1, B2 part is minus 9, 1, and minus 5, minus 1. Okay. And then I row reduce this augmented matrix, if you like, so that on the left I have the identity matrix, 1, 0, 0, 1. Why? Because I want to solve for the weights, right? I'm solving for the weights here. So on the left I have the identity matrix, and on the right, if I do these operations correctly, I should get 6, 4, minus 5, minus 3. Yeah. Okay. And now I can read off my results from the columns of this matrix. So thus, the C coordinates for B1 are 6 minus 5. And the C coordinates for B2, I'm just writing these out. We weren't asked to find these, although we have to find them on the way to this answer anyway, since these are obviously going to be the columns of this matrix. Okay, and once you know all the C coordinate vectors, then writing out, thus, the change of coordinates matrix from B to C is the matrix that has these as its columns. It's already visible right here. That's the point of doing it this way. So this is the 2 by matrix reading row-wise, 6, 4, minus 5, minus 3. Okay. So note, like, what did we get when we did this process, right? So what do we get? And once I write this out, you'll see how this works in general. So just set up matrix equation, right? Multiply by inverse. Oh, yeah, okay. No, yeah, exactly. So I was reading from the chat there. So the thing is that unfortunately, none of the work is done for you here, so you have to solve for those weights, and each of those, of course, is its own matrix equation. But because it's the same matrix in each of those, you can do this simultaneously. And so you could do this for any number. You can do this in any Rn. So the way that this works is, notice that when we wrote out that augmented matrix, C1, C2, B1, B2, right? Because our matrix in the matrix equation, the matrix that had column C1, C2 was there in both cases, and I had two different right-hand side vectors, B1 and B2, right? So when I row reduced this to identity, right, what was left on the right-hand side of that matrix, of course, was my change of basis matrix. And now this process works in Rn. So this process generalizes to Rn. And now once I have the change of coordinates matrix, I can just multiply any vector. If I have the B coordinates for that vector, I can just multiply by the change of coordinates matrix, and then I immediately have the C coordinates. So that's being able to find the change of coordinates matrix tells you everything. So this process generalizes to Rn directly. Okay, it's just more tedious, obviously, because there's more. These matrices are bigger. Okay, but this generalizes exactly. Yeah, so I was just reading the chat. So basically, the idea is that, just going back here real quick, we had these, let me make sure they're still on the page. So we had two matrix equations here, but the matrix was the same, right? So this is like matrix equations. We'll say it's like AZ is equal to B1 and AW is equal to B2, right? So if you have two of these and you want to solve them, right, because the matrix A is the same in both, you can solve them simultaneously by writing the augmented matrix A, and then when you write a normal augmented matrix, right, like, so ignore this second equation for a second. Ignoring that second matrix equation, if you were writing the augmented matrix to solve that matrix equation, you'd do that and you'd be done, right? That would be it. So you would augment this matrix. You'd have A here. The augmented part you'd be slapping the B1 column on the end. The idea, though, is you can actually keep track of what you're doing with these row operations on A by tracking what it does with both vectors simultaneously by just slapping on two vectors. And in fact, you could do this, right? If you had three, you could do this just as well, right? Okay, so you could do this just as well here with the augmented matrix. So there were some examples in chapter 1 homework. I just can't remember if I actually assigned any specifically, but there were some examples that was done in chapter 1 of this. But anyway, so this is the idea here. Okay. It's just a convenient way of organizing these matrix equations. But yeah, this process generalizes to Rn, so you can do this. You can do this in that way, so it's not a problem. Okay, and then of course, going back here real quick, revisiting this example. What if I needed to say go in reverse, right? What if I was, given this info as I am here, and now I want the change of coordinates matrix from C to B? Well, I just find the inverse of this. That's it, right? So, okay, so that's more or less all I wanted to say about that. So now you've seen it in the more general context of a more general change of basis between a B and a C, not necessarily where one is the standard basis. So that's the point here. Okay, so in the few minutes I have left, what I'm going to do is give you a motivation in case you haven't seen this before of eigenvalues and eigenvectors. So many of you will have seen eigenvalues and eigenvectors before in other contexts. So for instance, if you've already had differential equations, if you had 246 at UMD, then you'll have already seen eigenvectors and eigenvalues. There's plenty of other contexts in which these things come up. They're extremely, extremely important, but you might not have seen kind of it explained directly why you might expect eigenvalues and eigenvectors to be as important as they are. And so what is the idea? So eigenvalues and eigenvectors. I don't want to say the motivation, but I want to say a motivation for eigenvalues and eigenvectors. What is kind of the idea? Many situations arise in various fields. These various fields can be physics, it can be biology, it can be computer science, it can be in various fields. There are many processes that can be described or modeled by iterating matrix multiplication. So many situations arise in various fields that can be described or modeled via iterated matrix multiplication. What do I mean by that? Well, so let's say that I start out with some initial vector. Let's say I have some initial vector like x. Then maybe, so this is my time step 0. So maybe to get from my initial time step to the next, I would do ax. So this is my time step 1. And then to get to the next time step, I would multiply this by a. And so to get to successive time steps in this process, I would just multiply again by a on the left. Okay? All right. And so multiplying by a on the left here, well, I can rewrite this as a squared, right, times x. And what I mean by a squared, of course, a squared is a times a, right, using matrix multiplication. Okay. Yeah, and so continuing on, right, so this would be my second time step. Right, and so going to my next time step here, I would multiply again on the left by a, which would lead me to a times a squared, or a cubed, right? So a cubed, of course, is a times a squared, or a times a, however you want to write that, right? Matrix multiplication is associative, and these are just copies of a, so we're good here. Okay, and so on, right? And so, yeah, as Yekta was saying in chat, to get to the nth time step, right, you've just multiplied by a n times, right? So your nth time step is a to the n x. Okay? Now, there's a ridiculous amount of processes all over the sciences that can be described or modeled by a situation like this, okay? A ridiculous amount. And so, understanding the behavior of iterated matrix multiplication is important, okay? But there's a catch here. There's a problem, okay? So, the idea, understanding the behavior of raising a matrix to a power like this is very important. But for a general matrix, how do I understand this? So how can I understand this? Well, raising like a real number to a power like this is trivial, right? There's nothing to understand. But raising a matrix to a power like this is not trivial, because note, if I just take like a general example, so if I have a matrix A, and that matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Can you quickly compute like A to the 10th? Well, what is it? It's a 3 by 3 matrix, right? So it's a 3 by 3 matrix, but what does it look like? The question is it the 10th power of these things? Well, no, definitely not. Right? Definitely not. So, for instance, what about this entry? Is this entry 3 to the 10th? Is this entry 8 to the 10th? No, right? No, what is this thing? Right? The problem is that when you multiply matrices, right, you can't get, I mean, even something like, here, let's just do a quick example of, here's matrix 1, 2, 3, 4. let's do a times a, right? A squared is a times a. So I'm going to rewrite this. So 1, 2, 3, 4, 1, 2, 3, 4. So even for a 2 by 2, let's see here. So I have my first entry in this is going to be 1 times 1 plus 2 times 3. So that's 1 plus 6, so that's 7. And then the entry in my first row, second column is 1 times 2 plus 2 times 4. So that's 2 plus 8, so that's 10. Okay, and then my next entry is 3 times 1 plus 4 times 3. So 3 plus 12, that's 15. And then my last entry is 3 times 2 plus 4 times 4. So that's 6 plus 16, so that's 22. Right? So compare these entries to 1, 2, 3, 4, and you're like, huh? Like, what is going on here? Right? Again, it's very hard to see what is going on. It's very hard to tie that back to the original matrix. The idea is that this is a matrix raised to an nth power. Well, there's not a whole lot of data here in this n. That's just an integer, right? It's just a positive integer. Okay, so there's like no data there. So this should be, in some way, everything you need should be in the original matrix A. But, like, where is it? Right, look at this matrix. Look at this matrix A. Where do you see the entries or something associated to this matrix showing up in even the second power? Right, and of course, if I kept going, this gets even worse, and I just have no way of seeing what it is that's going on here. Okay, and so what is the idea? Well, let's do another example. Let's pick a matrix D, and let's have that matrix be 2, 0, 0, 0, 4, 0, and 0, 0, 1. Okay, what's D squared? You might be like, oh my god, it's a 3 by 3 matrix. But it's a nice 3 by 3 matrix, and it turns out that for diagonal matrices, well, it's easy to compute powers. Okay. In fact, I can easily compute any nth power of a diagonal matrix by just raising it to the entry. So this would be 2 to the n, 0, 0, 0, 4 to the n, 0, 0, 0, 1, right? To the n. I'll just do that for completion, but okay. So, wow, wouldn't it be really, really nice if we had a diagonal matrix instead of just a generic matrix? Well, yes, but I mean, in how many cases are you going to have something so simple that it would be modeled by a diagonal matrix? But that's exactly what eigenvalues and eigenvectors allow us to do. So eigenvalues and eigenvectors will allow us to describe when a matrix A behaves like a diagonal matrix for the purposes of iteration. Like a to the n. Okay. That's the key. Now, that might seem a little bit hand-wavy at the moment, but we will go over this specifically. This will be made 100% precise eventually. Yekta, so no, that's another thing. We are not going to be reducing it to... So this is the first chapter. As I said before, this is the first chapter where you're going to be doing something that is not reducing it to row echelon form, because reduction to row echelon form alters the eigenvalues. So row operations alter eigenvalues, and so this is a key thing, because any invertible matrix is row equivalent to the identity, right? And as we'll see, that would mean that every single invertible matrix would have the same. If row operations didn't change eigenvalues and eigenvectors, all invertible matrices would have the same eigenvalues and eigenvectors, and they definitely don't. Okay, so yeah, echelon row operations are not going to be useful for us here. Okay, so we will have to do other stuff, okay, to analyze these things. Anyway, so that is that is it for today. So I will see you all on Friday, where we will properly start Chapter 5, which is eigenvalues, eigenvectors. So we'll be doing this for a couple of weeks. It'll probably take us maybe like 2 weeks to get through all of Chapter 5. And then we'll be getting into Chapter 6, after which we'll basically be done with the course as it is. So the things that we cover in Chapter 7, basically we cover like one thing that is universal among all courses, and then after that, whatever time we have left, we basically spend on whatever we want. So I'll probably do Jordan canonical form and maybe, I typically, when I teach this course, have a couple of days for fun stuff that I'll do at the end. So yeah, I'll probably have at least 2 lectures for fun stuff. But we're closing in. We're definitely entering, after Chapter 5, we'll definitely be entering the home stretch for the course. But anyway, I will see you all on Friday.